part of an effective data science workflow is being able to acquire and distribute data efficiently. In this video, we're going to focus in on methods for tabular data. First up, we'll look at how we can load in tabular data into our working environment in R. As we've seen already, an Excel spreadsheet isn't the only possible file extension to use when working with tabular data. We actually have a preference for simpler, more open source formats that allow us to improve the accessibility and reproducibility of our workflows. These are things like CSV, TSV, and plain text files. And we're going to consider how to read each of these into our working environment. To demonstrate reading in each of these file types, we're going to load in some example toy data. This is going to be in the form of random data.csv, .tsv, and .text. These data files all contain the same information, and this should say it contains 26 observations of 4 variables. There's going to be an ID, which is just a Roman letter from A to Z that functions as an identifier. There's going to be a column called Gaussian that contains standard normal random variates, a column called Gamma with Gamma 1 random variates, and Uniform with standard uniform random variates in it. So this really is some random data. If we wanted to read this tabular data into R using base R functions, then we'd use the read.csv function, and this takes a single argument that is the file path to that data, and here we're storing that in a random data frame. And here we're storing this in an object called random_df. What we can see here is that the output is a data frame type object with 26 entries, and really all this data frame is a collection or a list of vectors with some nice methods associated with it. So here we have a list of length 4 with named elements called ID, Gaussian, Gamma, and Uniform, but because it's this special data frame object type, we've got nicer ways to interact with that object. This isn't the only way though that we can read tabular data into R. The read R package gives us a whole range of functionality for reading in various different data types. The way to read in a CSV file here, very similar to the base R method, we're going to use the read R function called read_CSV. Very subtle difference there. And the argument this takes as its primary input is exactly the same. It's just the file path to the file that you want to read in. What's different here is the type of object that's output. It isn't a data frame anymore, but it's a tibble object. And this is an object that you might not have come across before. But this is exactly the same as a data frame in that it's a list of vectors with some nicer methods associated with it. So here we can see that this is a 26 by 4 tibble, and we get some additional nice properties here, like the truncated printing, where it shows us that we've got 10 rows visible here in the head, but 16 more rows that we aren't seeing. It also points out the type of each column, so ID is a character, and every other column is a double. So what are the benefits of using read R over base R to read in a CSV file? Well, firstly, there's an associated increase in speed of an order of about 10 times, depending on the file type in your operating system. First up, there's an increase in speed of about 10 times, depending on properties of the file in your operating system. And for very large files, if it's taken a while to read in this CSV, we'll give you a progress bar to tell you how far along that loading is going. The second really nice property is that strings aren't automatically converted into factors when you use the read_CSV function. There's a way of doing this in base R, but that requires you setting the argument strings as factors to false, where it's true by default. So this reduces one thing that you have to do and one thing that you have to remember each time you read in a CSV file. Thirdly, the tibble doesn't support row names. So in the same way that a data frame can have column names, you can associate row names with it that aren't within the table, but they're associated with each row. This is to make sure that all of the data in each entry in your table is stored within the table itself, rather than as some additional attribute to the table. And additionally, tables allow us to use some slightly more varied and nicer column names at times. Additionally, tables have slightly looser rules about what can and can't be a column name, which can be quite helpful if you're reading in some messy data. Finally, you get a bit of a reproducibility bonus by using tables, because when using read.csv, the base R function, some of the ways in which that functions are going to depend on the operating system that the function's being run on, whereas the read_csv function is specifically designed not to depend on the operating system. So the next few slides are going to be dedicated to what they forgot to tell you about tables. The first thing that I mentioned briefly before is that the default printing method is much nicer than for data frames. By default, it's only going to print the first 10 rows and as many columns of that table as will comfortably fit onto your screen. This can sometimes be not what you want to do, so you can adjust this behavior within the print call by setting the number of rows that you want to print, n, and the number of columns within the print call. Here, if you want to print 3 rows and all of the columns, you can set n equal to 3 and width equal to infinity. An additional bonus that you can't really see in these slides is that you get some really nice colour formatting when you're printing tables in an IDE that makes them a lot easier to read, but that doesn't come through in these slides. Another big benefit of using tables is that they're stable to subsetting. Whenever you extract information from a table, it's always going to return another table. And this is really useful when you're working with tables or data frames within functions, because it means there are fewer awkward edge cases that you can run into. So, for example here, if we think about taking a row out of either a table or a data frame, in both cases we're going to get the same object type back. However, if we're looking at column subsetting, so taking a single column out of a table or data frame, a table gives us an n×1 table back, but a data frame will give us an n vector instead. And we run into this same issue when we look at combined subsetting to just pull out a single entry, where this will give us a 1×1 table or a single value. It's much easier to write stable code when you know the type of object that your subsetting is going to return. So readr doesn't just provide us functionality to read in CSVs, it provides many more functions for reading in different types of data, and it gives us additional arguments to these functions that can be really helpful when we're reading in messy or non-standard tabular data. So if we're reading in tabular data, we've got equivalent read functions for TSV files that work in exactly the same way as a CSV. But we've got a more general function called read_delim, which can read in any delimited file. This might be where entries are separated by a space, a tab, a colon, whatever you like. You specify the delim argument to say what is separating your entries within each row. As well as reading in tabular data, it's useful to be able to write out tabular data from your working environment. So this might be to store intermediate results, or even have data as the final product of your data science workflow. The functions to do this are entirely analogous to the read functions from readr. We're just swapping out the word read for the word write. One thing to be aware of is that this 10 times speed up that you get by using readr over base R functions is sometimes just not going to be enough. In some cases, you might have lots and lots of data set to read into memory that individually are each very large. So reading in each file takes quite a bit of time. If it's the case that each of these individual files still fits within your computer's working memory or RAM, then I'd really recommend you check out the data table package, and in particular the fread function within that. And this is specifically optimized to read in tabular data as quickly as possible. This can be really useful if, for example, you're working in some sort of simulation study where you have to load in a single large data file, apply some process to it, and then repeat that to many of these large data files. There is, of course, the other case where you have one very large file where that exceeds the amount of RAM that you have. And this isn't going to be covered in this course, but there are methods for dealing with that, both within R, where you load a portion of the file at a time, and outside of R, using things like databases to handle these sorts of summaries more efficiently. In the second part of the video, now that we've got our data into R, we're going to have a discussion about what it means for our data to be tidy and for it to be in a nice form to analyse. Before we get on to tidy data though, let's take a slight aside to discuss the differences between wide and tall data. And we'll see this first by two examples. So in this first example, we're storing the exact same information in two different ways. In the left-hand side, we have a wide format, and in the right-hand side, we have a tall format. In the right-hand side, we've got one row for each person. On the left-hand side, we have one row for each person and one column for each observation. While on the right-hand side, each person is repeated multiple times so that we have a single row for every value that is recorded. Similarly, in our second example, our observation unit is no longer a person, but it's a team, and we have an example of wide data on the left and tall data on the right. You can see that we've got the same sort of structure going on here. In the wide data, each observational unit is included only once, and in the tall data, each observational unit is repeated so that each recorded value has its own row. Really, this is the difference between wide and tall data. In wide data, the first column has unique entries, and this needn't necessarily be the first column. I'm referring to the column that identifies your measurement unit here, the thing that you're taking measurements of. In tall data, on the other hand, this ID column has repeating entries and unique rows for every observation. What we have here is a trade-off. While wide data is easier for humans to read and compute on, it's much harder for machines to compute on this wide style of data. And this is flipped for tall data. This is much easier for machines to work on and harder for humans. So one of the key skills that you're going to need as a data scientist is being able to pivot between these wide and long data formats. And the reason for this is that the types of error that are most common are going to be different when inputting data and when analysing data. When you're inputting data, you might want to do this in a wide format where it's much easier for humans to understand as they input each entry. And while analysing the data, you might then want it in a longer format where it's easier to perform your manipulations and you're less likely to make mistakes at that stage. So being able to switch between these long and wide formats is going to be useful to control our overall errors within our analysis. Again, we're going to use a package to help us do this, and it's going to be the tidyr package. And in particular, two functions from this package. One called pivot longer, which takes wide data and lets you move it into a longer format, and pivot wider, which takes long data and helps you pivot it into a wider format. We'll see an example of this coming up soon, but first let's take a minute to discuss what we mean by tidy data. The concept of tidy data can be summarized in three key principles. The first of these is that each variable should have its own column within your data frame, or tibble. Each observation should have its own row within your data or tibble. Each observation should have its own row within your data frame or tibble. And each unique measured value should have its own cell, and every cell should contain such a value. These three properties are the defining features of tidy data that make your information much easier to process when you're working in a tabular form. So you might have heard of the concept of tidy data before, but what's often forgotten is an explanation of why you want to have your data in this tidy form to begin with. The first major benefit is the consistency that it provides. Knowing exactly the structure of any tabular data set that you're going to work with is going to reduce the cognitive load that you place on yourself, and it also allows you to develop specialized tools or functions to efficiently work with tabular data in this tidy format. This lets you make really quite efficient tools and implement them without causing too much mental strain. You don't have to remember whether each row was an observation or each column, for example. The particular reason of having the columns be our variables in this case is kind of particular to R. The reason here being that R is a vectorized language. It works incredibly efficiently with doing things like matrix and vector manipulations, but isn't quite so great with things like for loops. By keeping your variables as columns, you allow those columns to be really efficiently extracted and manipulated from your tables or data frames. For example, when you're creating new columns as functions of the old ones, or when you're subsetting your columns to keep only entries that have certain values. Again, this sort of efficiency comes back to the idea that data frames and tables are a list of vectors, rather than being a true matrix-like object. So let's see a couple of examples here of pivoting wider and pivoting longer. In this first dataset, we have a wide format where each column gives the country ID and then the year of observation. The rows then correspond to different countries, and the values within the cells are giving us the number of cases. If you try and make a time series of this data, you'd really have quite a lot of hard work to do, because the year values that you want to plot on the x-axis are trapped within the variable names themselves. To make this data tidy, what we need to do is pivot it into a longer format. We're going to turn these column names that describe the year into a new variable that we'll call year, and we want to retain each of these observed count values in a separate column called cases. To do this, we're going to use the pivot longer function, and we need to tell this function which column names we want to convert into the values for our new column. So we're going to convert the 1999 and 2000 column names into a new column called year, and we're going to take the values within our table currently and store those in a new column called cases. This gives us something that is much easier to work with when we're creating a time series plot for these. One thing to note here, and this is related to the idea of tables allowing special column names, is that these quotation marks around 1999 and 2000 aren't single quotes, they're actually backticks. And these work like escape characters to let you call columns within a table things that aren't valid data frame names. So in a data frame, you could never call a column 1999 in the first place, but in a table that is allowable. And the way that we extract these columns using their names is to quote the names using backticks. In our second example then, we'll see some more non-tidy data, and this is the data that we've seen already. It's the teams data that we saw earlier. You might want to take a minute now and just ask yourself why this example isn't tidy. Go ahead and pause the video if you like. So the reason that this data isn't tidy is because each observational unit in this example is one team. For our data to be tidy, we want each variable to be stored in a separate column and each cell to contain the values of those variables. At the moment, we have one column that describes all variables, and the values are stored in a separate column. So what we need to do is pivot this into a wider format in order for it to be tidy. When using this pivot wider function, the first argument we need to specify are the ID columns, and this is the column that is going to uniquely identify each measurement unit. So in this case, it's going to be the team. We then need to specify which column we're taking the names of our new variables from, and in this case, it's just going to be the column named variable. And finally, we need to specify which column we're taking the values of those variable measurements from, in this case, helpfully named value. Here we should be a bit relieved to see that what we recover here is the wider version of this teams table that we had earlier, and this is now in tidy format. So these pivot functions that we've just met, pivot wider and pivot longer, are going to resolve issues with untidy data where those issues arise in the rows. This might be that there are too many observations per row, or too many rows per observation. Similarly to these, there are equivalent helper functions to solve the same problems in columns rather than rows. So it might be that your data isn't tidy because there are multiple variables per column, in which case the tidyr function called separate is going to be useful. And it might be the case that there are multiple columns per variable, in which case you're going to want to unite those columns using the tidyr unite function. The final thing I'd like to talk about here is how missing values link in with tidy data. We've said already that in a tidy data frame, every cell is going to contain a value, and this is going to include all cells with missing values. But how do you encode a value that is inherently not there? In R, this sort of missingness is denoted by the NA object. This might either be the generic NA that isn't type specific, or a specific version of that, such as NA underscore character underscore, to say that you know that something's missing here, but the thing that is missing is a string. This might equivalent be an NA integer or an NA double or some other data format. When you're reading in data with missing values, the readr function also really comes into its own, because the read functions have some pretty good defaults to help identify where these missing values are. And in the case where the function isn't getting it right, or you've got a really strange encoding of missingness, they've got an additional argument called NA that is really useful in letting you specify how your missing values are encoded within your tabular data. A little note on data collection here is to try and influence whoever is collecting or recording this data to encode NA values in some sensible way. And the key here is really to avoid ambiguity. So if a cell that is missing is just left empty, there's no indication of why that cell is empty. Is it that the machine didn't record the information correctly? That the person didn't show up at all? Or that this value just isn't appropriate for this individual? An empty string tells you nothing about that. Putting in an NA value means that you at least know that the recording process went correctly, but there wasn't a value to be recorded. One way you can add in extra information here is to add a notes column to each row, where the data collector can add additional information to describe any missing values or any oddities about that observational unit. Two things to really avoid when coding NA values is using numeric values, because there's nothing to say that this isn't an anomalous observation that really does have a value of -999, for example. And really worst of all is encoding missing values as a 0, because in so many situations this is incredibly easy to overlook and could lead to large biases in the conclusions that you're drawing. We'll come back and revisit the idea of missing values and how you can handle them during the exploratory data analysis videos. So wrapping up then, reading in tabular data is now something that we can do by a range of methods, and we can also write that data back out to CSV, TSV, or text files. We also introduced the idea of a tibble and how it differs from a data frame, as well as the concept of tidy data and how this differs from wide and tall data. One thing to note here is that tidy data is a good common standard, but it's not always going to be the best way to work with your data. For certain data types, it might not be possible to store it in a tabular way, or in certain fields, there might be conventions about how to store data that differ from this. Again, consistency is the key here, so if you're working in a field where this isn't the standard way of storing and working with data, for example, there are some bioinformatics and mapping files that are stored in very particular ways that don't lend themselves to useful analysis within a tidy table, then go with that standard data type. Don't force this into a situation it's not intended for. That being said, this tidy data structure is appropriate. You should make every effort to use it, because there are very good existing tools for tidying messy tabular data, and then operating on those tidy tables once you've created them. Thank you very much for your time, and I'll see you in the next video.